Hi there, this is a question from the 2017 Exam 1 from the Geometry and Measurement module of the exam. So question 8, three circles of radius 50 millimeters are placed so that they just touch each other. The region enclosed by the circles in the circles is shaded in the diagram below. The area of this shaded region in square millimeters is closest to. So with this question, what we're trying to find is this shaded region in there. Whenever we work with whenever we work with circles, we need to always remember that a radius is from the center of a circle to anywhere on the outside of a circle. So for example, a radius of here to here would be 50 millimeters, and a radius of here to here, if it was straight, would be 50 millimeters as well. So this point of this circle to this point of this circle is 2 radii. So that would be 100 millimeters. Then we could go again from this point to that point, and then that point to that point would also be 100 millimeters. And then from this point to the edge and then to the center is another 100 millimeters, because each of these sides is made up by two 50 millimeter radii. Now, our next point is that if we have a triangle that has all the same sides, this is called an equilateral triangle. So an equilateral triangle has 3 same sides and 3 same angles. So inside these 3 angles are all 60 degrees, because 360s make up 180, the inside degrees of a triangle. So now what we could do is work out the area of this triangle, and then we can subtract later other calculations of areas to leave just that middle shaded section. So the formula for the area of a triangle, I'll just put in here, we've got 100, we've got 100, and we have 100. The area of a triangle is, if you've got an angle and the two sides that make the angle, is half times BC times sine A. And that formula, the angle A, is the angle made by the two sides that you know. And luckily in this question, all our sides are exactly the same. So put into your calculator, 0.5 times 100 times by sine 60. This calc comes out to be an area of 4,330.127 millimeters square. Now remember, don't round off too early, only round off right at the end of the question, because those parts of the rounding might actually affect the answer. So now what we have is we have the area of this triangle here. Another formula that we have is the area of a sector. So right in here, if I change the color, just quickly, change the color, right in here is the area of a sector. And we also have 3 areas of a sector, which are going to be all the same areas of the sector. So an area of a sector, is the formula pi r squared times by the degrees that make the sector over 360 degrees. So we can work out one area of the sector and then multiply it by 3 to find out the total 3 areas of the sectors. So let's put that in, pi times 50 millimeters squared times by our angle of 60 from our equilateral triangle over 360. This answer turns out to be 1,008.996939. Once again, keeping millimeters squared, keeping all our decimal places along the line. We then have 3 areas of that. So we can do our answer, and if you're using your scientific or your CAS calculator, keep that answer in, push ANS on your calculator, and it stays there. And our answer times by 3 would give us the total area of the 3 sectors to be 3,926.990817 millimeters squared. We are nearly there. The area of the triangle, and we have the area of the combined three sectors. Now what we want to do is if we take the total area of our blue triangle and we remove the areas of the red three sectors, that will leave us the area of the space shaded in the diagram. So we would do 4,330.127. We would minus our answer that we just calculated of 3926.990817, and this would leave us with the solution of 403.131618 millimeters squared, which the answer is closest to a 403. If we look at our assessor's comments for this, question number 8, only 35% of the cohort managed to get this one correct, quite evenly spread across B and C. The key for this answer, being able to identify the shapes inside this diagram and then identifying formulas that we have for those shapes. So whenever you have circles, using the radius to calculate the length, the key word here is that they are just touching each other. So we could work out the length from the center of the circles, identifying it's an equilateral triangle, using the correct formula for the area of a triangle, and then identifying that these are sectors. So using the correct formula for area of a sector and then subtracting the appropriate values. Hopefully this one helps for your upcoming exams.